Because what comes after the ABCs? No, what comes after ABC? D, exactly. So that's what we're going to introduce today, is the D. I know, it really sucks. Okay, so once again, we're going to continue our calculations, basically the Feynman calculus. We've got a sort of an idea of how it works based on that toy model, the ABC toy model. And what we're going to aim at today is actually taking the Feynman approach and steering it towards a more realistic approach, which is basically going to start with QED. Hence, the ABCs are going to have to meet Dirac, which starts with a D. Hence my cute-ass joke. Thank you very much. I appreciate all the laughter. Thank you, I appreciate it. Okay, so first and foremost, obviously, the Lagrangian we started with last time is different than the Lagrangian that governs QED. So I really need to revisit the Lagrangian we started with last time and show you actually how you would extract the Feynman rules, or the elements of the Feynman rules, from that Lagrangian, and then we can apply the same prescription to the Dirac Lagrangian. So very quickly, just recall from the ABCs, the Lagrangian was the sum of three terms, and I'll just say sum over A. 1/2 d mu phi A d mu phi A minus 1/2 ma c over h bar squared phi A squared. So there's basically three of these. Okay. Actually, let me say these are I's versus A's. I'll make it a little bit more easy. And then we ended it all with a coupling term of minus g phi A, phi B, phi C. So maybe I will go from A to C in my sum. Sorry. Okay. Now, in calculating diagrams, remember, we built them from lines, propagation lines, labeled by the particle type. And then we use the vertex. Okay. Where we used minus ig for vertices, or vertex factors. And then we used I over qj squared minus mj squared c squared for virtual particle propagators. Okay, so if you remember, we might have been evaluating a diagram like this, where this is A, B, C, A, B. Okay, and to write down the expression for m, which is the magnitude, you would basically take two vertex factors, one for here and one for here, and then you would use one virtual particle propagator, because you only have one virtual particle, that's C. These A's and B's are real. These go out to infinity, they live forever. But this guy, he obviously is born and dies. Okay, that's BD vertices. I'm just kidding. But he is. He's born and he dies. So he's virtual, so we have to give him a propagator. Of course, all of these external particles have propagators, but those are parts of the Fermi golden rule, so don't worry about that. Okay? So now what I want to do is I want to show you how you could get these factors directly from this Lagrangian. And of course, the way that you do that is through quantum field theory, which we're not going to teach or learn in this class, so I'm just going to set them down as rules. So here we go. If ever you have a Lagrangian, I'll give you the general rule and then I'll apply it to this to reproduce these factors. If ever you have a general Lagrangian, then for the vertex factors associated with interactions, because remember vertices indicate interactions in any Lagrangian, you write I times the interaction term in the Lagrangian, so this is what we would call the interaction term L interaction. You multiply I by that interaction term in momentum space, where to get to momentum space, we basically replace I h bar d mu with p mu. Or we can replace just d mu with minus I over h bar p mu, the same thing. Okay? And then erase the field variables. Okay? So let's see how this plays out in this story. So first of all, we want to write I times the interaction Lagrangian. So in the ABC example, we would do minus I G phi A phi B phi C. Okay? We write it in terms of momentum. So we take any derivatives that are present and turn them into p's, but there's no derivatives present. So we don't really do that in this case. And then we just erase the field variables. That is, we just come in and we erase phi A, phi B, phi C, and boom, there's the vertex factor, as promised. Okay? And then for propagators, we do the following. We write the relevant, and I say relevant because in this theory there's only one, but in the theories that we'll be dealing with there's more than one, so you just have to write down the relevant one. But you write down the relevant free particle equation of motion in momentum space, and we lose the overall factor of h bar. Okay? So for example, in the ABC case, we have d mu 5 for any of the phi's plus mc over h bar squared phi. Okay? So we want to write that in terms of momentum space. So we're going to replace, once again, d mu with minus I over h bar p mu. And if we do that, and we also notice we're going to introduce the factor of 1 over h bar squared when we replace these d mu's with p mu's, because each d mu gets a factor of minus I over h bar, but particularly 1 over h bar squared. We're going to have 1 over h bar squared here, and that's what we can ignore. Okay, so just eliminate that, and then we'll be left with basically p squared minus mc squared on phi equals 0. Okay? Then, and it's just going to be a simple story like this one, we multiply the inverse of the term in brackets by I. Okay? So if we took this and we found its inverse, and then multiplied it by I, we would get I over p squared minus mc squared, which is exactly our propagator. Here we call the momentum Q because we label internal momentum as Q. This could be Q or P, it doesn't matter. So I could call this Q just for comparison's sake. Because you're only going to write down these factors for the internal virtual states, and we generally label their momentum as Q instead of P. That way we know what's external, what's internal. It's a little bit easier to organize. Okay? And of course, we do this for each field. So if this is phi A, then this is A. That's why the J's in there. Okay, it's just if you have more than one virtual particle, then you have to give it specific labeling. Okay? So are there any questions about this process? Now, what I want to stress is that in words, this and this are exactly what we're going to do in quantum electrodynamics. The equations are going to be different because we have a different Lagrangian to start with. Moreover, we're going to have a lot more work in actually evaluating these things, but it's the same in words. Okay? So can I erase this? Thank you. All right. So I know I'm going to regret doing this, but let's just do it. So let's consider the QED Lagrangian. L is I, H bar C, psi bar, gamma mu d mu psi, minus MC squared psi bar psi, minus Q psi bar, gamma mu psi a mu, minus 1 over 16 pi d mu a mu minus d mu a mu, d mu a mu minus d mu a mu. Okay? Notice this is the spinor version of the kinetic term. Along with this is also part of the kinetic term. This is, of course, the interaction term. Notice it's an interaction term because the spinor field psi are coupled to the gauge field A. Okay? And then this is, of course, the kinetic term for the gauge fields. This only involves factors of A. And it's a quadratic term, so it's just a kinetic term. If there were 3 factors of A multiplying each other, then that would be an interaction, or 4 or 5 or 6. But if you only have quadratic terms, notice when I multiply this out, I only get quadratics. Quadratic terms just contribute to the free particle Lagrangian. Okay, they're not interaction terms. Right? Notice this is quadratic inside. This is our only interaction term. Okay? Now, the fundamental vertex, well, it kind of comes from this term, and I'll just go ahead and draw it, but we'll have to put in we'll have to figure out what the vertex vector is in just a moment. But basically, you kind of already know this story. You have a particle coming in, and now is where we're going to have to identify on the line whether we're talking about the particle or the antiparticle. In the ABC story, the antiparticles were the same as the particles, okay? However, we know that there are anti-electrons, positrons. And so we need to indicate whether we're talking about an electron or a positron, and the way that we do that, this is the important note, is the direction that we put on the arrow. Okay? So let me just draw this real quick. This is a photon, this is an electron, this is an electron. This is the basic interaction vertex of quantum electrodynamics. It just says that this electrically charged particle can emit or absorb a photon. Okay? We can build interesting processes out of this, but this is the fundamental vertex. Okay? Now I just want you to realize that is basically the same diagram. All I've done is I've sort of flipped it over. You can flip, twist, you can do anything you want with these diagrams, as long as they've got 3 legs. One of them is a photon and the other 2 are the same. But this is an anti-electron giving off a photon, and you get an anti-electron out. Does that make sense? Okay? So this is what I want to just point out is I'm just going to call the thing an E because it's basically an electron, but if the arrows on the lines are flowing to the right, it's an electron. If the arrows on the lines are flowing to the left, it's an anti-electron. That's why we're now going to use these arrows on the lines. We're also going to have momentum arrows, but remember momentum arrows are always next to the line. So that's, it's going to get kind of complicated in notation. Okay. You might notice that I don't have any arrows on the photon lines, and that's because photons are equal to antiphotons. There's no distinguishing them. So no need for lines on photons. Okay, now the I times this thing is of course just I L interaction, which is minus IQ psi bar gamma mu psi a mu. Okay? And then all we do is we remove the field variables, psi, and A, okay? But unfortunately, removing A, we have to repeal to a dimensional argument, so I'm just going to give you the final result. So we remove psi bar and psi, those are straightforward, but then we remove, instead of just A coefficient h bar c over 4 pi times a. Okay? And of course you can do that because you can write a, we can just write this as minus iq psi bar gamma mu psi square root 4 pi over h bar c square root h bar c over 4 pi. A, that's just a factor of 1. And now I'm going to eliminate this, this, and this. This is what I'm going to be left with. Okay? So at the end of the day, we're going to find I root 4 pi over h bar c q gamma mu. It's the factor that, oh, sorry, minus. Okay? This is the vertex factor that we'll use in QED, and this is the only vertex in QED, so don't worry about it. Okay? Well, I will say one thing. The Q in this expression is the charge. Okay? Fortunately, in most calculations with QED, the charge is 1. Okay, we'll just call the electric charge 1. Okay? The only place where that story changes is when we do QED with quarks, because quarks have fractional charges. Okay? But we'll worry about that later. Okay, we'll just do quantum electrodynamics for leptons right now. Okay? And then we can actually clean this story up a bit by just defining a quantity GE. And so this is going to be IGE gamma mu. Okay? Where GE is obviously a combination of Q squared 4 pi over h bar c and a minus. All right? So anytime we're trying to evaluate a Feynman diagram with quantum electrodynamics in it, for every vertex, we write down this factor. Okay? Now, for the propagators, it's a little bit more of a headache. For electrons, so these are vertex factors, and then we have propagator factors. For electrons, positrons, because so let me just go ahead and argue this. Think about it. I can imagine a diagram that looks like this. Okay, that's a contribution to a scattering of something and something into something and something. And for this diagram, I'll have to draw an internal propagator for the photon, right? Everybody see that? Okay. I could also consider the interaction of a photon with a charged particle. Okay? Where in this story, I would have an internal or a virtual electron or positron. So I need the internal propagators for both photons and for electrons or positrons. Depends on the direction of the arrow. Okay? So let's work them out first for electrons and positrons, and then we'll do photons next. So following the prescription that we gave before, we're going to write down the free equation of motion for these particles. Okay? And now what we want to do is we want to send this to momentum space and get rid of the h bar factor that arises, in which case this is going to be gamma mu p mu minus mc psi equals 0. Okay, remember we just replaced d mu with minus I over h bar. And now, to figure out the propagator, we basically just multiply the inverse of this expression in brackets by I. So that is clearly going to be gamma mu p mu minus mc inverse, which happens to be I gamma mu p mu minus mc, plus mc over p squared minus m squared c squared. Okay? Literally, this is a scalar. Well, it's actually not a scalar. It's technically not a scalar because gamma mu is not a scalar. Okay? But you can say the inverse of this is basically this expression. You can check that by multiplying them together and doing all the operations. Okay? Okay. Now, for photons, this story is a bit more of a headache. But just for generality later on, let's start with the massive Proca equation. Remember, in this case, the fields are spin a half, so we're using the Dirac. And for the photons, those are spin 1, so we use the Proca. Okay, and it's basically the Proca equation, which comes from varying this and setting the variation to 0 with respect to the A field, and then you get an equation of motion for the gauge field A, and that's going to include the free Proca part. So the Proca equation is d mu A nu minus d nu A mu plus mc over h bar squared A nu equals 0. Okay? And I am not going to spend a lot of time trying to derive this. I'm just going to give you the two results. But this gives us two interesting results. There is the m not equal 0 case, which will actually, and the reason I'm showing it to you is this case will be useful when we eventually do the weak interactions. Okay? By the way, much of what I'm saying in this story, especially with regards to these propagators, that same story is going to play out when we're doing QCD and the weak interactions. Because in those parts of the diagram, like, these vertices are going to depend on the interaction. I mean, they're interactions. Okay? But the propagators don't care about the vertices. They're just a particle moving through space. So these propagator factors are going to play the same role they're playing here in the same form when we're doing QCD and the weak interactions. That's why I want to go ahead and give you the non-mass, or the mass doesn't equal 0 version. Okay? All right, so for m not equal 0, then what we're going to end up with is we're going to have a factor in here, and I'm going to write it down, but this is going to be minus I over p squared minus m squared c squared. That's pretty easy. Times a to mu nu minus p nu over m squared c squared. Okay? So it's almost as simple as what we had here, except we got an a to mu nu and a p nu. And then for the massless case, don't think that you can take this expression and just instantly choose the mass to be 0. It's not that simple. But what you'll come up with in this case, and one of the ingredients in the massless case, which is what actually keeps you from going to infinity when you take m to 0 in that, is applying the transversality. So when you have a massless gauge field, its polarization states are transverse to its direction of motion, versus if it's massive, it has three polarization states. But don't worry about that degree of difficulty. This just simplifies to minus I a to mu nu over p squared. Okay? So in the case of QED, this is the photon propagator. Which of course is useful when we're talking about processes that involve virtual photons. If it's an external photon, we don't use this. Okay? Instead, in this case, we would use this propagator. All right. Okay. Now let's let it get dirty. Now, we've got these factors. Now, Tanner's not here, is he? Tanner? I don't think so. Tanner's not here. Oh, Shaylee, you're on there. So yeah, you can answer this question. Man, I gotta turn all these Tanners over because he's not here, damn it. And maybe I'll take off all of his class participation grade for this. Just kidding. All right, Shaylee. What did we do with all of these factors in the ABC theory to calculate m? M is what we're after. Once we have m, we just stuff it into Fermi's golden rule.
We followed the steps and added the factors depending on the...
well, we didn't, did we add, well, oh, go ahead, say what you're saying.
Oh, depending on the picture that we drew.
Sorry, say it again?
Like we drew a picture and we like followed the picture and elements of the picture told us where to put those factors.
Right, and in particular, like for this one right here, our factors included two vertex factors and an internal propagator, and what else? Do you remember?
The delta function?
Yeah, you just basically had delta functions which conserved momenta. And you say, delta P1 plus P2 minus Q1 and delta Q1 minus P3 minus P4. And then that's just making sure that the momentum is conserved at the interaction vertices. Okay? So you put vertex factors in here, you put internal propagators in here, you put these delta functions, and then you integrate over all of the internal momenta. Do I need to write this down, or do you all roughly remember this? You did a calculation with this last time, remember? Okay, all right? Now here's a very important thing which Shaylee is going to remind us. In the ABC theory, what kinds of objects were we working with in terms of how they transform in space-time? Starts with an S and rhymes with scalars. What do you think? Scalars, awesome. That's great. Yeah, the ABC theory was based on scalars, and I said this to you. I said, with scalars, basically everything commutes. So we really didn't pay attention to the order in which we wrote down things. I mean, we obviously put the integral sign on the far left and the D4Qs on the far right, but we just jumbled shit inside of here and didn't really worry about the order, right? Well, guess what? This is a theory of spinors and vectors in space-time. It's not going to be that easy, okay? At the end of the day, we have to make sure that the magnitude that we calculate itself, m, is a scalar, okay? So that's kind of the rule we're going to use to dictate what we should be writing. It will make sense eventually, okay? But it's just a complication to doing this, which is a real headache at first. And then you're like, it's kind of work. Okay, so, yes. Okay, so I'm going to start out by giving you an array of expressions which will be useful, and then I'll actually go through the rules for QED, but I'm going to have to get these expressions up here first, and I guess I'll just erase this and write them up here. Yeah, we'll do that. We've already gotten our vertex factors and our propagators, so you've hopefully written those down. Now I'm going to give you an array of useful factors. And of course, what I'm aiming at today is to basically get the building blocks for Feynman diagrams and QED done, and to give you an example of the start of a calculation. And we'll quickly realize that there's a couple of hurdles that we have to get over to finish the calculation, and we'll start our analysis of that today, and we'll finish it up next time. But, okay. So, some useful expressions. I'm going to first of all give you wave functions for electrons, positrons, and for photons. Okay? So for an electron, we can say that psi of x is an amplitude a e to the minus I over h bar p dot x, where that's p mu x mu, times a spin factor us p. Okay? Where all I want you to notice is that this coefficient factor, a is a constant, it's not going to do anything. But this thing is just saying I want to consider a plane wave. So this is just talking about the propagation of the spinor. This factor is where all the love is, because this factor is responsible for this being a spinor versus a scalar versus a vector. Okay, I'll remind you of what these look like. These are basically solutions to the Dirac equation. okay, assuming a plane wave form. But what's a pain in the ass about them, in contrast to the non-relativistic story, which you've seen before, is that the spinors actually depend on the momentum. And I'll write down some expressions reminding you what those spinors look like in a moment. If you have a positron, the expression is very similar, but I'm introducing some notation here, so pay attention. In this case, it's a e to the I over h bar. So again, positrons can be interpreted as a reversal of time flow. P dot x times what I'm going to call VSP. Okay? And we'll scoot photons over a bit. Okay? So once again, the positrons, they have an overall plane wave form when you're talking about their propagation, and then the V is going to describe their spinorial properties. Okay, and I'll talk about S and P in just a moment. And then for photons, we'll have A mu of x equaling A e to the minus I over h bar P dot x. Of course, we're going to assume plane wave forms for these as well, times epsilon mu. Okay. All right. So, yeah, and actually, I don't know why I'm writing these. These are not subscripts. These are functions of momenta. Sorry about that. Okay. So epsilon mu is telling you about the polarization of the photon. So remember, photons, they wiggle in a particular direction. And this vector is just telling you about the direction in which it's wiggling. And this is telling you about the propagation. Okay? This does not depend on the momentum. In these cases, though, these are telling you about the spin polarization, but these depend on the momentum p. Okay? Now S, mu obviously takes values 0 to 4, but S takes values 1 and 2. We just need 2 degrees of freedom for these spinors. All right? All right, so we're going to need the equations of motion in momentum space for each of these. We obviously need these as part of our prescription. So we're going to have gamma mu p mu minus mc u equals 0. And then we'll have gamma mu p mu plus mc v equals 0. Okay. And then we'll have p mu epsilon mu equals 0, and epsilon 0 equals 0. Okay. All right. For the adjoints, we're going to have u bar equals u dagger gamma 0. V bar equals V dagger gamma 0. And we'll just use epsilon mu star. Okay, so if our polarization of the photon is described by epsilon mu, then an adjoint of that is epsilon upper mu star. Okay. And then we can talk about the adjoint equations of motion. Of course, written in momentum space, in which case we're going to get u bar gamma mu p mu minus mc equals 0. V bar gamma mu p mu plus mc equals 0. And then we're going to have p mu epsilon mu star equals 0. And you can also set the 0th term to 0 as well. Okay, now here are 2 important features that those u's and v's and epsilons are going to satisfy. First of all, there's an orthonormality condition. So we can say if I take an adjoint with some corresponding spin s, and I contract it with the original with spin s prime, then this is going to give me 2mc times delta ss prime. Okay? So basically I'm looking at the condition of contracting an adjoint with a spinor And it's basically saying it's 1 if they have the same spin polarization, so if they're both 1s or they're both 2s, and it's 0 if they're different. Okay? Of course, we can say very similarly for the positron spinors, except we insert a minus. Okay? And then for the photon polarizations, we're going to have epsilon mu s, epsilon mu star s prime is minus delta s s prime. Okay? Now, don't worry if this doesn't make a ton of sense. Okay? I'm going to give you the forms of these u's and v's in just a second. And once you have the forms of those, you can actually prove this. Because you can just take the adjoint, multiply it by the original, and you'll get a delta function. Okay? So don't worry about deriving any of this. Just you can show it based on the expressions for u's and v's, and then just plug them in these expressions. Okay? I say that. On the other hand, we're going to use this extensively. So just look at it for a moment. U bar U is a delta function over the spins. V bar V is a delta function over the spins with these coefficients. Okay? Now, there is yet another very useful expression that comes out of this story, and that is completeness. And the completeness says, if I sum over the spins with factors of US and U bar S, then what I actually get is gamma mu P mu plus MC. Okay? And if I sum over the spins with VS, V bar S, I get gamma mu P mu minus MC. Okay? Now you might be wondering, why are you summing over spins? What does that do? This is kind of like, it's kind of like a resolution of the identity. You know what you do in quantum mechanics? You take a sum over projections of the wave function, and that'll basically act like the identity. Well, we're not really going to use these as identity. Actually, when we do calculations, we'll find that we rather often sum, or actually we almost always sum over the spins, for reasons we'll get to later. But we're basically almost always going to sum over the spins. Well, actually, I can motivate it right now. I can just tell you. You want to do calculations that give you the number that you want to compare to experimentally. I mean, you can calculate anything you want, but calculating numbers that they actually measure in a lab is a more fruitful enterprise. Now, here's the thing. When they do experiments in the lab, they normally they normally send in particles without any polarization. So that means that the ingoing particles, you don't say that this is spin up and this is spin up. Rather, you sum over all the possible ingoing things. So you could do spin up, you can do spin up, spin down, you can do spin down, and spin down, and spin up. So when you're doing the calculation to compare to what you're getting in the experiment, you sum over all the polarizations of the ingoing particles, okay? Because you're basically sending in a beam which is not prepped for a particular polarization. However, on the outgoing part, you want to average over all of the polarizations, okay? Because once again, we're not measuring the outcoming polarizations, okay? So that's why these sums are going to play an important story later, but we'll talk about that more when we actually get to the calculations. All right. Whew. Now, just to show you where you might extract these, and to give you a distinction between what I wrote down formally versus what we need to use now, I'm going to give you the expressions for the spinors, solutions to the Dirac equation. Again, we changed our convention when we started doing the Feynman rules. So I gave you a list of the convention changes, like the metric changed. Now it's 1 minus 1 minus 1. There's a few other changes. Now I want to give you the new forms of these so that you can use them if you need them in a calculation, like proving these. So U1 is now going to be square root of E plus MC squared whoops, over C. I'll just do that. And then it's going to be 1, 0, C P Z over E plus MC squared times C PX plus IPY over E plus MC squared. Okay, that's the U1. And then we can do the U2. They're all going to have the same prefactor. Well, they're always, almost, yeah, they're going to have the same prefactors, actually. So now we're going to have 0, 1, and then CPX minus IPY over E plus MC squared minus CPZ over E plus MC squared. Okay? And then for V, yes?
Slightly larger.
Okay, I'll write the next one really, really big, but you know, you can always look at my notes and track them down, but I'll write the next one really big. E plus MC squared over C times C, it's kind of fun. I might have to erase this very shortly. Minus CPZ, oh whoops, I have to, here, I'm just going to sneak in a little E plus MC squared. Oh, this is a shit show. Minus CPZ over E plus MC squared, 0, 1. Okay, there you go. There's that one. And now I'll write V2. I took all my room over there, so I can't draw it that big. I mean, you can't complain, man. Okay? But what's important is, you know, I'm kidding. I'm not going to write this big, you can read out of the notes. There's a minus sign in front of this one. Otherwise, it has the same coefficient. It's basically the same structure, but I've got 1, 0 on the bottom instead of 0, 1. Okay, hopefully you see the theme. What's really changing when you go from here to here is you're changing these two, and then you're interchanging these two with a minus in there, you know. And the same happens on the positron. Okay? If you hadn't asked me, I would have drawn them all same size, but anyway, it doesn't matter. It doesn't matter. Okay. All right, and for spinor matrices, just in case you don't remember, gamma 0 now is basically 1, 1, minus 1, minus 1, and the gamma i's are 0, sigma I, minus sigma I, where the sigmas are the Pauli matrices. Okay, and I'll write the Pauli matrices in my notes, but we're not gonna need to do it right now. Okay, so these are a lot of the important ingredients, and now it's time to give you the rules for the Feynman diagrams in QED. Because so far I've just given you some essential ingredients. These will obviously be useful later, or these will be useful later on, although it's not obvious. But now it's time to actually write down the rules for QED and crank out at least an example or two before we leave. Okay? Everybody all right? Just trust me, just put in a space filler for these, and then you can either figure them out from these, or you can actually figure them out from these, or you just look at my notes. Okay, I'm gonna have to erase all this. Sorry, I need it in. All right, here we go. The QED rules. And the good news is, about half of them are exactly the same as in the ABC story. The bad news is that the other half are different. All right, so I'll see what I can do here. I don't know if I can do anything, but I'll see. So first of all, you want to draw the diagram. And label matter lines with arrows. Okay, so remember, that is an electron, whereas that is a positron. And you do this for any electron or positron in the diagram, but you don't do it with photons because they're their own antiparticles. Okay? And then, of course, just like we did before, you want to label momenta external via P's. Those are incoming. They start out at infinity and then they come in and they are ending in an interaction vertex. So these are the incoming particles. These are real particles, so they get labels P. And then, of course, you could do outgoing. Notice my momenta labels, or the arrows indicating the direction, are not on the line itself. That we reserve for identifying what kind of particle is propagating. And of course, these are, once again, a long time. These are external momenta. They definitely go forward in time. Okay? But for the internal case, we can do either direction, okay? Or, of course, if we're doing internal photons, we can do Q or minus Q. It doesn't matter. Okay? So these are internal particles, matter particles, electrons, positrons. These are internal photons. Okay, and again, you're going to use Q for the internal momenta and P for the external momenta. All right. Now, here is something new, quite new. And I'll try and stick to here. I'm going to regret this in just a moment. Each external line gets a factor according to the following picture, all right? So this is the body of the interaction. This is the part that we'll fill in with many different diagrams. I'm just going to label the external particles. So we could have an incoming particle, or we could have an incoming antiparticle, or we could have an incoming photon. Likewise, on the leaving, we could have an exiting particle, an exiting antiparticle or positron in this simple case, and an exiting photon. These are just the three possibilities, okay? So anytime you have an incoming particle, your expression for M is going to get a factor of U. Okay? Anytime you have an exiting particle, not an antiparticle, but a particle, you're going to get a factor of U bar. Okay? For antiparticles, it goes exactly in reverse. For a leaving antiparticle, you're going to get a factor of V. Whereas for an entering antiparticle, you're going to get a factor of V bar. If you try and interpret this in time, it's kind of backwards. It's U bar, and it's V bar V. But if you do it in terms of the flow on the lines themselves, this is incoming, this is incoming. You just have to decide whether you're going to do the particle flow or the evolution in time, which you'll stick to evolution in time. And then for photons, if you ever have an incoming photon, you want to put down a factor of epsilon mu. And for exiting photons, epsilon mu star. Okay? Now, here's an important observation. There's an important detail when we're actually applying this. So you want to number factors with momenta. Okay, so what do I mean by that? Well, basically it's kind of simple. You know, we might have a collision, or we might have, you know, a diagram that involves two incoming electrons. Okay, something like that. For each of these incoming electrons, I'm going to have to write down a factor of U. Somehow I'm going to have to designate one of the U's with this and one of the U's with this. The simplest way to do that is to say, okay, well, I'm going to assign this electron momentum 1, or P1, and I'm going to assign this electron momentum P2, and then I can just say this is U of 1 and this is U of 2. So the 1 and the 2 here is just a label telling you which of these particles this is the spinor for. It's just a concise notation, okay? So I just want you to realize though that these labels of 1 and 2 are not affiliated with the S's up there. Those are affiliated with the spin direction. But these are actually associated with this labeling by P. So this is the P1th term and the P2th term. We'll just call them 1 and 2 for simplicity. No need to keep writing P1 and P2 everywhere. Again, this will make more sense when I actually put it into a calculation. All right, so now let's go on to step 3. And this is where it gets easy. Each vertex gets a factor of I, G, E, gamma, mu. Okay? Now, well, actually, I'll just keep on. Okay, so internal lines. And we picked this up from before. Electrons, positrons. They get a factor of I, gamma mu, Q mu, plus MC over Q squared minus M squared, C squared. And the photon, again, gets a factor of minus I, eta mu nu, over Q squared. Okay? So those are the propagators we've already derived. Okay, 5, we want to conserve for momentum at each vertex with delta functions. Okay, so that's the same thing we did in our ABC story. We're just conserving linear momentum. So at each vertex in the diagram, we just put a delta function of all the ingoing momentum minus the outgoing momentum. All right. Step 6, integrate over internal momenta. Step 7, it's the same as it always is, cancel overall 2 pi to the 4th delta 4 p total in minus p total out, and multiplied by I to get m. Okay? So you'll notice quite a few steps are the same as the ABC theory. This one's kind of weird though, right? What did we use for the external particles in the ABC theory? How do we label those? Huh?
Just like momentum.
No, that's part of the thing you're going to stick it into. Okay, but in the expression for M, did we write anything down? The answer is no, because that was a scalar theory. These factors, U, V, and epsilon, these are just the polarizations of the spin and the vector angular momenta. So these are non-zero, or they're not identities, or they're not numbers, scalars, okay? They're transforming quantities, okay? So this is sort of a brand new thing in this story versus the ABC story, okay? Here is a step 8, though, which we have to take into account, basically due to the fact that we have particles and antiparticles. So what we want to do is we want to antisymmetrize between diagrams related by switching to incoming electrons / positrons, okay, or to outgoing electrons, positrons, or one incoming electron, positron with one outgoing positron / electron. Okay? And I'll give you examples of this in due time. All right? Now, there's actually a rule 9, which you can't really do at the end. You actually, it sort of tells you the flow in which you should be, or the order in which you should be writing things down. Because that's one thing I haven't said to you yet is, well, what order do you write things down? Okay? Well, first of all, we need to kind of realize which elements of this story are non-trivial. Like scalars, you can always move around. But let's figure out which elements of this story are non-trivial. First of all, this is a picture, but here we're going to write down these factors for the external momenta, or sorry, for the external states. Are these scalars? Is U a scalar? No, what is it? It's a spinor. Yeah, it's a space-time vector, okay? What kind of quantity is that?
Doesn't it have both vector and spinor?
It's a vector in space-time. What is it in spin space? It's a matrix, okay? So this is a matrix in spin space. It's a vector in space-time. Ooh, okay, what about this? Scalar? You think? Well, look, there's gamma mu.
But
Okay.
something is Q.
That removes the space-time part, but it's still a matrix in spin space. Okay? What about photon propagator? It's a tensor in space-time. This is the metric, but a metric is a tensor in space-time. This is trivial in spin space, but it's non-trivial in space-time. Okay? All right? So clearly, we've got matrices in spin space, we've got spinors, we've got things associated with space-time transformation. So we've got to be really careful in how we write things down. All right? But it gets even better than that. Because I don't know if you remember, but when we were dealing with the space-time transformations, where I said, if you're going to do it by matrix multiplication, you got to write it down in the right order. It very quickly said, screw matrices, let's use the Einstein summation convention. And that way, if you want to do A mu, B mu, you could always reorder them. And you'd always get the same thing. Okay? Maybe I should add an extra thing on there. But anyway. However, and I promised you this earlier on when we introduced spinors, for spinors, we're not going to use an Einstein summation convention. We're just going to use the idea, okay, that spinor is sort of a row, this is a column, and then we got spin matrices which have to be stuffed between them. Because the one rule that we know is that to get a scalar, you basically always have to have a row matrix and a column matrix, and you can put square matrices in between. You don't have to, but you can. This thing will give you a number, where what I'm talking about is spin space. This is a row spinner, this is a column spinner, and then this is a matrix in spin space. Okay? The reason we don't do this sort of, we'll just assume matrix multiplication for space-time, is exactly because we can encounter things with more than two indices, which can't be represented by matrices. But it turns out that all of the spinorial quantities that we're dealing with either has one spinor index, that's the u's and the v's, so those are either going to be these row or columns, or it's a matrix in spin space, like the gammas. Okay, those will be represented by matrices. Okay, so what we want to do, and I promised you this a long time ago, I promised you my misspelling, is we want to create spinor sandwiches. All right? So we want to write down row spinners, some spin matrix, and then a column spinner. We might have more than one of these in our final expression. Okay? But this is basically going to govern how we're going to put these factors together that we've written down. Okay? Now, so does this make sense? Because now I'm going to give you some details on how to do this, and then we'll just go through a really quick example. Let's go. So what we can say, start with an outgoing matter particle. So that would be labeled by U bar. Remember, this is matter, this is antimatter. An outgoing matter particle is a factor of U bar. Or an incoming antiparticle, V bar. Okay? And then what you want to do is you want to follow the lines which connect either the outgoing particle or the incoming particle throughout the diagram. And as you encounter vertices, you write down a vertex factor. Okay? If you have an internal line, you draw the internal line factor. You write it down. If you have another vertex, you write down another vertex factor. But eventually, any outgoing matter particle will stem from some incoming matter particle. So you'll end ultimately with outgoing antimatter which will of course be indexed by V, or incoming matter. And again, this will make a lot more sense when I give you an example. That's when we get to it. Okay? So again, this is for the spinor part of the story. That's where the real complication comes in. For the photons, you can put their epsilons pretty much anywhere, because we're using Einstein's summation convention on the mu's, and they're trivial in spin space. So the factors for the photon, the epsilon mu factors, you can kind of put them anywhere. Okay? All right, so let me just, without any further ado, let me just get, oh shoot, go for it. Two hands.
Well, like an incoming U always have an outcoming U bar? Or
You'll see in a moment, I promise.
just want to make sure that it's basically saying you follow it through the diagram
Yes.
until you get to.
Yeah, let me actually just do this in an example, and I think it'll be a lot clearer, okay? So I'm going to erase all this from my example. These quantities will become very, very useful in our next lecture, because we're going to get a basic starting expression for m, and then we're going to have to do a lot more digging in order to calculate what its actual value is, and that's where we use a lot of those. But let me just get through a simple example. So let's do E plus E goes to E plus E. So we can write down two diagrams contributing to this. First of all, we can do this one. And then I'll label my momentum P1, P2, P4, P3, and then I don't think, oh, I didn't do a Q. I'll figure out which direction I did Q in just a moment. Okay, so here we go. I can start, well, first of all, this is matter and matter. There's no antimatter in this story. So I can start, for example, with, we'll do this one first. So here's an outgoing matter particle. So I can write down a factor of U bar, and we'll label it as being associated with the particle with momentum P3. Okay? Now, if I follow this line in, the first thing I do is I hit a vertex. So I should write down a vertex factor. I, G, E, gamma, mu. Okay? Now, the simplest thing for me to do is to just go out this guy. That's an incoming matter particle. So that gets a factor of U, and this becomes U1. So I've basically followed an outgoing line to an incoming line, and in the process made a spinor sandwich. Okay? So that's for this line tracing. Then we can trace this line, and we'll do very similarly. We can do U bar 4, I, G, E, gamma, U2. Okay? The only tricky part is here I labeled the matrix associated with this interaction as IG gamma mu. This is a different vertex, so I need a different label. Well, I'll just use gamma nu. Okay? Notice both of these are spinor sandwiches. This is a row spinor, this is a spin matrix, and this is a column. Same here. Okay? So those are scalars. The only last part of this story that I have to throw, well, there's a couple of parts. The important next part is the propagator of the photon between these two vertices. And this I can actually write anywhere because it's trivial in the spin space, but I'll just write it in between them for completeness. Minus I eta over q squared. And now I just have to get the indices on eta right. Okay? Well, I want this thing to be a scalar in spin space and in space-time. I've got a mu index and a nu index. What indices do you think I need to put on that metric factor? Mu and nu, exactly. All right? And now the rest of the story, you know how it plays out. So we're going to do form momentum at the vertices. So we're going to do P1, and I'm doing the Q this way. Okay. Minus Q minus P3, 2 pi to the 4th, delta 4, P2 plus Q minus P4. Okay. And then we can, of course, do, and sorry, we're going to also integrate over D4Q over 2 pi to the 4th. Okay. I can, once again, use the delta functions. I can use one of them to do the Q integral. What I'll be left with is the delta function after I've used maybe this delta, which one do I use? Yeah, I'll use this one. If we use this delta function to evaluate the integral over Q, then I'll rewrite this delta function, but when I rewrite this delta function, that's just going to end up giving me that delta function from the P in to the P out, and that's what I erase, and then multiply by I. So at the end of the day, the M from this is going to be U bar 3, I, G, E, gamma mu, U1, U bar 4, I, G, E, and of course I could factor out the I, G, E's, those are all just constants. U2 times minus I, P4 minus P2 squared times I. Okay? Now, this is not the only contribution to this quantity. There's another one. Can you tell me what it is? Okay, so I saw a suggestion, maybe this. Well, let's try and work it out. This is an incoming electron. Is that an incoming electron? Is that vertex allowed? No. Remember, the vertices always have to have an incoming electron and a leaving electron. Or if you turn the diagram on its side, it's an incoming electron and an incoming positron. If you think about it, this interpretation of things conserves charge. Photons have no charge, so whatever's coming in to create a photon has to have a net charge of 0. That's an electron and a positron. Here, the photon is emitted with no charge, so the charge incoming should equal the charge outgoing. Everybody see that? So unfortunately, this is not a contribution to this process. The other contribution is actually this. Remember this from last time? Okay. I just want you to remember from last time, the M associated with this can be very different than the M associated with this. These are not the same diagrams. Okay, and you can really hang that on how much momentum is being transferred for a given value of the external momentum. But at any rate, if I call this diagram 2 and I just call this one diagram 1, so we'll do 1 and 2. Notice M2 is equal to M1 with 3 interchanged with 4. I mean, really and truthfully, if I take this diagram and I want to evaluate this one, all I do is I interchange 3 and 4 everywhere. What that means is that the total M should include M1 minus M2. There should be a relative minus sign between them. That's the antisymmetrization argument. Okay? All right, we'll stop there. We'll have plenty more to pick up after our quiz on Thursday. But are there any questions before we depart? Yeah.
Why is it an overall minus instead of summing them to get the total out?
Sorry, here?
Right, so the main M, you get that by summing all of the individual cases.
Yes.
So why are we subtracting from here?
We're subtracting them because these two diagrams are related by the interchange of two outgoing electrons. That's this rule 8.
So that's something separate from just accounting for all of that.
Yeah. Okay. Any other questions? I'll see you guys on Thursday.